Okay. Hi everybody. So last time we did another knights and knaves puzzle. Did you figure out the answer? So here was the puzzle. You see 3 islanders from that island of knights and knaves, where people either always tell truth, the knights, or always lie, the knaves. And you see 3 people from that island talking to each other, Arnold, Bob, and Charlie. You ask Arnold, are you a knight? But you can't hear what he answered. Actually, that's kind of not a good question to ask somebody from the island, as you'll see. But suppose you did. But then something more informative happens. Bob pitches in. Arnold said he's a knave. And Charlie says, oh, don't believe Bob, he's lying. So can you figure out who is who? Can you figure out who is Arnold, Bob, Charlie? Who is a knife, who is a knave, who is telling you the truth, and who is lying? Let's see. So first, let's say what Bob said that Arnold told you. Bob said, Arnold said he's a knave. Well, let's see, is it even possible? If Arnold is a knight, would he say he's a knave? Well, no, because that would be lying, and knights don't lie. And if Arnold was a knave, he wouldn't say, I am a knave either, because that would be telling the truth, and knaves hate telling the truth. They just never ever do it. So there is no way Arnold could have said, I am a knave. That means Bob is lying, and if Bob is lying, Charlie is telling the truth. We have no idea whether Arnold is a knight or a knave. There is not enough information, but just by hearing Bob say, Arnold said he is a knave, we can immediately say, Bob, you're lying. And Charlie saying, Bob is lying. Okay, Charlie, we could trust you. So the thing to pay attention to here in the logic terms is that the sentence A, if and only if not A, is a contradiction, no matter what A is. Whether A is true, whether A is false, whether A is just one proposition, whether A is a huge formula, A, if and only if not A, just a contradiction. It's always false. So with that in mind, let's look at simplifying formulas. Why do I bring up simplifying formulas once we talked about knight and knaves? Because imagine that in knives and knaves that A, if and only if not A, was for A some really big and complicated formula. Would we need to write a truth table for that big and complicated formula? No. As long as we know that the very topmost thing says A, if and only if not A, we know the whole thing is false. And we really don't care what happens inside of the A itself. So today I'm going to tell you some ways that we could simplify formulas, make them smaller, sometimes make them formulas on fewer variables, so we could have a smaller truth table, and sometimes even show that your whole formula is always true or always false. So we just saw it last time with negations. If you have a negation on the outside, we could use double negations in De Morgan's to propagate it lower and lower and lower in the tree until all negations are on your propositional variables. So for example, if you start with a formula A and C implies not B or C, you could simplify it like we did in last class by using definition of implication and De Morgan to this formula on the second tree here, which would be not A or not C, or not B or C. And today I'm going to tell you what kind of logical equivalences, what kind of rules we could use to simplify such formulas even further. So think about doing arithmetic. A lot of things in logic have analogs in arithmetic, even though some things behave quite differently. If you have 3 plus 4 plus 5 plus 6, it really doesn't matter whether you compute this sum by taking 3 plus 4 equals 7, plus 5 equals 12, plus 6 equals 18. Okay. Or you could do it as 3 plus 4, 7, plus 11, that's the same, 18. So no matter in which order you do those summations, you're going to get the same answers. And in fact, probably you would write it without parentheses. Just 3 plus 4 plus 5 plus 6 is the same no matter which order you do the operations. Similarly, if you have only multiplications and nothing else, 3 times 4 times 5 times 6, you could do in any order you want. There is the same phenomenon which is called the associativity rule. You could associate every number with the one to the left or to the right if you have an operation such as plus repeating several times. And in logic, you could do it with or and and when they repeat. Moreover, sometimes we even represent it on a tree by drawing just one node with or and connecting all the things to it. You just say it's an or of a whole bunch of things. So either not A, not C, or not B, or C. One of those should be true in order for the whole thing to be true. In some of the other classes later on, when you're doing Boolean circuits and hardware, you will see a lot of this, because the way things are often implemented in hardware is you have one hardware gate, for example, the OR, where you have lots and lots and lots of wires. It really makes things much more compact. So what do we gain by doing this associativity rule and replacing the 3 ORs with one OR? So before we go further, remember another thing about addition and multiplication. 3 plus 4 plus 5 is exactly the same as 4 plus 5 plus 3, or 4 plus 3 plus 5, whichever order you want to do it. And again, this rule, called commutativity rule, that switching things around if you only have the same kind of operation doesn't change the answer, also applies to logic. If we have something or something or something or something, we could take those subformulas and put them into the OR in a different order, and the answer would still be the same. So here's how we could use it here. What if we switch the two parts of the tree that we have? One part where we have node C, node C, and another part where we have B. What if we just switch the order? Then we get not A or not B or not C or C. Now, if you look at the very last part, the not C or C, this is something that will be true no matter what value of C is, for similar reason why A, if and only if not A, is always false. Either this is true because C is true, or this is true because not C is true. And we know that in logic, one of them always has to be true. What does it tell us? Well, we can ignore the rest of the formula because it's connected to this thing by an OR, and just say, oh yeah, it's true because it tells me something, 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 or true. The whole thing must be true. So here are the rules that we looked at so far. We saw commutativity that allows you to switch the order of the variables. A or B is the same as B or A, and similarly, A and B is the same as B and A. We looked at associativity, which allowed you to do the operation in whichever order you want, because the result of taking OR of A and B and OR of that with C is the same as taking OR of B or C and ORing that with A, and same for AND. And this looks familiar because the same rules apply to addition and multiplication. There is another rule that applies to addition and multiplication, this time two of them together, is that you could factor out things, or you could expand things, you could put things inside parentheses, you can take them out. If you have 3 times 1 plus 2, that's the same as 3 times 1 plus 3 times 2. Same thing holds in logic. If you have A or B and C, this is the same as A and C or B and C. Again, think about or as sort of like a plus and sort of like times. But in logic, you could do more. In arithmetic, if you have 2 times 3 plus 1, you could never get it in a form 2 plus 1 times 3 plus 1. In logic, because the rules here are a little bit different, we can do this. So in logic, we have that really strange looking rule from arithmetic perspective, which is a dual rule to the previous one, which says A and B or C is the same as A or C and B or C. And we call those rules, again, both in logic and in arithmetic, distributivity, because you distribute that value of C between the two parentheses. Here is another set of properties that we just used, because a lot of time we are really happy when we could say, oh yeah, this whole big thing is true, so we can ignore the complexity of the individual pieces. Or the whole big thing is false. Or the whole big thing is repeating, so we could just throw out a part. And here are the rules. Again, think about them as common sense rules. You could always derive them using a truth table that really tell you how to do things. For example, if you have something that's true, or anything will be true. Because in order to make an or of things true, it's enough for at least one of them to be true. Similarly, false and something, the whole thing would be false. Now, if you have something false or something that you don't know, it's the thing that you don't know that will tell you whether the or altogether will be true or false. So if I say 2 plus 2 equals 5, or today is Tuesday, then it may be true if today is indeed Tuesday. It may be false if today is Wednesday. But overall, the value of the whole thing will be exactly the same as the value of proposition today is Tuesday. And you can completely ignore 2 plus 2 equals 5 because it's just false. So similarly, true and something has the same value as this something. True and A has the same value as A. And what we just used was how do we get those things that are always true and always false to begin with. A simple way to get them is to say something or its negation is always true, something and its negation is always false. If I say today is Tuesday and today is not Tuesday, you really don't care if it's Tuesday or not. You just know what I said is wrong. If I say, well, today is Tuesday or maybe today is not Tuesday, you may say, well, why do you even need to say it? You didn't give me any information whatsoever. What you said is true no matter what. And finally, one more useful property is when we find repeated things, we could shrink them by throwing out the repetition. If I say today is Tuesday or today is Tuesday, well, you know, it's just today is Tuesday. If I say today is Tuesday and today is Tuesday and today is Tuesday, I only need to say it once, right? And it will have the same truth value. So finally, let me just, for completeness, throw on the slide the two rules that we used in the last lecture. One of them, the double negation. If you have not A is the same as A, it's not that today is not Tuesday. Well, yeah, today is Tuesday. And another one is the De Morgan's laws. Not of A or B is not A and not B. Not of A and B is not A or not B. So let me just do a very quick example to show you at least how the distributivity rule, the weird part of it, works. So suppose you have a negation of that formula, A or not B implies not A and B. The previous steps you've seen before, a negation of F implies G is F and not G. Now you got the not on the inside, then you start doing your De Morgans and double negations until you come to A or not B and A or not C. Now, with the rule that we just did, we can simplify it a little further if we want to, by taking a outside the parentheses. So we could factor out a and get a or, not b, and not c. Again, this is a form of distributivity that is not true for arithmetic, but for logic, and an or are much more symmetric than plus and times in arithmetic. So we can do it. So let me show you another puzzle before we finish this lecture. Suppose I like one of the shapes, either triangles or circles. Suppose I just like one of them. I like triangles, don't like circles, or like circles, don't like triangles. And I like exactly one of the colors. Maybe I like the blue things, or maybe I like the yellow things. And I'm not picky, so I like something if it either has my favorite shape or it has my favorite colors. Suppose I tell you that I like blue triangles. What can you say about the rest? So think about it for next time.